And represented here, you might be able to see some windings of wire coming around on the top. They come around along the bottom. And we've actually separated it up into 1, 2, 3, 4, 5 separate coils of wire so you can see what's happening in the interior of the solenoid. If the current comes in from the power source here and goes in this direction, then the magnetic field will be toward me. If the current goes in the opposite direction, then the magnetic field will be toward you. But the strong magnetic field will be in the interior of the solenoid. And we'll visualize that magnetic field using these black iron filings that when I energize by pushing this button, when I put a current through this coil, then these iron filings will line up in the direction of the magnetic fields. So what we'll be looking for is iron filings that line up like this and come around and then back and back in again. The iron filings, you won't be able to tell by looking at the iron filings whether the magnetic field is this way or this way in the interior, but you should be able to see that it's lining up along the axis of the solenoid. So I'm just going to hold this button down for half a second or so I don't burn out these wires, but hopefully you'll be able to see the filings line up. Okay, there's a little bit of alignment there. Yep. And you can see definitely the alignment of the particles coming through the center of the solenoid, starting to come back around the outside. The field is much weaker along the outside, so it's more difficult to see alignment of the filings outside. But especially here, you can see the filings aligning. So that's a magnetic field produced by a solenoid.
All right.
Solenoids are important in some auto lock type.
I don't care why he thinks they're important.
See the filings align.
But what I want you to see here is that this looks like a magnet. Okay? So we know a magnet, if I had a bar magnet, okay, we have a north and we have a south. The magnetic lines look like this. And they're very strong along the magnet. A solenoid allows us to create a magnet that we can turn on and off. Or we can vary in strength. We can do lots of things with this magnet. You can see they have these different coils, and you can see that the magnetic field inside is very uniform. That's what we want, a very nice, clean magnetic field inside the solenoid. So if we get rid of the magnet here, and instead we put a solenoid, okay, we get the same magnetic field when we run a current through here. And we can change the current to change the magnetic field and do all kinds of fun things. We in this lab don't care about the direction. It follows the right hand rule. I don't know if you saw him only using his right hand. So if the current goes around this way, the solenoid points in that direction. If it goes around the solenoid this way, it would point in that direction. But we don't care about that. Oscar, I assume you don't have your phone out in front of your iPad? Okay.
No, he doesn't.
All right.
It takes 90 seconds for this NASA-engineered AC cool down your room. It's smaller than a toaster, cools any room in 90 seconds, and uses just a fraction of the energy of a regular AC. This incredible...
It knows that I was looking at air conditioning units this morning.
Hey there guys, Paul here from engineeringmindset.com. In this video we're going to be looking more into solenoids and how they work. We're going to look at permanent magnets and how to see their magnetic field. We're going to create an electromagnet from a wire. We're going to be looking at some real-world solenoids and we'll also cut one open using some power tools. And finally, we're going to learn how to build our own basic solenoid. If you are working with solenoid valves, you're going to want to download the Magnetic Tool app from Dan Voss, who have kindly sponsored this video. The app makes it easy to test that your solenoid valve is working properly and works with both AC and DC versions. You can download it for free for Android and iPhone using the link in the video description below. So we'll start off by taking a look at a standard bar magnet. This is a permanent magnet. You've probably seen these type before. They have their ends marked. One end will be N for the North Pole and the other end will be S for the South Pole. We can use its magnetic field to move other objects. If we imagine this iron nail as a piston in a valve, then we can see that the magnet can be used to move the piston. The problem with this type of magnet is that the magnetic field can't easily or practically be turned off. So in this case, the nail will stay attached to the magnet until we physically pull it off. If we place two of these magnets together, we will see that the likewise polar ends will repel each other, but the opposite polar ends will be attracted to each other. If I then place a compass near the magnet, we see that as I move the compass along the perimeter of the magnet, the compass is being affected by its magnetic field, and the compass face will rotate to align with the opposite polar end of the magnet. You'll see it also follows the magnetic field lines. Remember, opposites attract. We can see these magnetic lines if we place the bar magnet down on a sheet of white card, and then we sprinkle some iron filings over the top. The iron filings are aligning with the magnetic field lines to create this pattern. These lines always form closed loops and they run from the north to the south. As I mentioned, the problem with permanent magnets is that they are always on and they can't easily or very practically be turned off or controlled. However, we can control an electromagnetic field, and we can generate that with some standard wire. Let's have a look. If we take this standard earthing wire and strip away the outer insulation, we find some copper wires inside. I'm just going to remove this with a sharp knife. Once it's removed, I'll just peel off one of the smaller wires inside. If I place a compass near the copper wire, we see that it has no effect on the compass. However, if I now connect a power source to each end of the wire, we see that as soon as I pass a current through the wire, the current creates an electromagnetic field, and this will change the direction of the compass, just like we saw with the magnet. The electromagnetic field is operating in a circular pattern around the wire. If I place some compasses around the wire and pass a current through it, you see that they all point to form a circle. If I reverse the direction of the current, then the compasses will point in the opposite direction. If we now take the wire and wrap it into a coil, we can intensify the magnetic field. I'll just wrap this around a screwdriver and then compact it until it looks something like this. Now if I connect a power supply to the coil and pass a current through it, we see that the compass will be affected and it now points at the end of the coil just like it did with the permanent magnet. When I move the compass around the perimeter of the coil, the compass will rotate to align with the magnetic field lines. If I reverse the current, we see that the magnetic poles will also reverse. When current flows through a wire, it creates a circular magnetic field around the wire, as we saw a moment ago. But when we wrap the wire into a coil, each wire still produces a magnetic field, except the field lines will merge together and form a larger, stronger magnetic field. We can tell which end the north and south pole will be for a solenoid coil by using the right hand grip rule. This says that if we grip our hand into a fist around the solenoid and we point our thumb in the direction of conventional current flow, that's from positive to negative. It actually flows from negative to positive, but don't worry about that for now. But if we point our thumb in the direction of conventional current flow, then the thumb points to the north end, and the current will be flowing in the direction of your fingers. So if we have current flowing in this coil from positive to negative, so from left to right, then the current is flowing through the coil towards us, and the north pole will be on the rightmost end. We can check that because the compass will face the opposite direction. Remember, opposites attract. So one compass points north for the coil's south pole, and the other points south for the coil's north pole. If we then reverse the power supply, so the current is flowing conventionally from positive to negative, so from right to left, we simply flip our right hand over. The current is now flowing away from us in the coil, and our thumb points in the direction of north. Our compass points north to the coil's south pole, and the other points south to the coil's north pole. If we now look at this real-world solenoid valve, we see on the bottom there's a metal valve body, and on the top is the solenoid within the blue box. So let's cut this one open and see what's inside the solenoid. I'll just place this one into the bench vise, and then I'll use the angle grinder to cut it open. I'll make one cut along the front side, and then I'll rotate it and cut down the other side. There's a few sparks coming out because we're cutting through metal on the inside. And there we go, this section has been cut out. If we look inside, we can see it's a pretty basic design with no moving parts. It looks like there's a solid copper ring inside, but that's just from the cutting blade. If we poke at the coil region, we will see it's actually a whole load of small copper wires all tightly packed together. With a little nudge, they would all fall out. Here's a much smaller real-world example without the protective casing. It's essentially the same, just a much smaller design and for a different application. If I connect this to a power supply, we can see that the piston can be pulled in by the electromagnetic field as soon as current starts to flow through the coil. If I cut the power, then the spring will force the piston back to its original position. I can remove the insulation tape to show that it's just a coil. If I then reassemble the solenoid and connect it to a power supply, we see that the piston is moved by the magnetic field and the spring. So now that we know how one works, let's make a very simple one ourselves. I'm just going to use this pen as the core body for the solenoid. I'll just cut this down.
We
so
don't
it's
need
short
to
again.
make
I'm
one
going
for
to use an angle
ourselves.
grinder
I
to
just
cut
wanted
this
you to
for
see
no
how.
real reason other than I'm just being lazy and I like using.
The idea here being to understand that now we can create these electromagnets. So we'll watch a few minutes of this one. Oops. I think this is
M1 to or
further
M21?
on in the video. I can do this. No, I can't. YouTube is hard.
Hello friends,
No, stop.
back to a new video on physics and animation. In our previous videos, we have learned about self-induction. In today's video on electromagnetic induction, we will understand mutual induction. And with this, our series on electromagnetic induction will be completed. As we learned in our previous videos, the coil generates a
So, we have a voltage source. This is a DC voltage source, which means it's the same current the whole time. Goes through a coil, creates this magnet. Okay? This is a really important idea. So, June, can you make sure you follow along?
Yeah, I am.
I know. I need you to be watching the video as well. Because it's not just the audio, it's also a visual.
EMF in response to the changing magnetic flux within it, which opposes the change. This phenomenon is called self-induction. Today our topic is mutual induction. To understand today's video, let's first take two coils, C1 and C2, which are placed close to each other on the same axis. And the galvanometer is connected to the second coil. When we pass a changing current through coil C1, such as alternating current, it creates a changing magnetic flux. When this changing magnetic flux links with the coil placed nearby, according to Lenz's law, an EMF will be generated in the second coil, which will cause the current to flow in a way that opposes the changing magnetic flux in the second coil. We can observe this current through the galvanometer.
So I want to make sure we understand what's going on here. Now we don't have a direct current, we have an alternating current. So this is a turning on and turning off magnetic field. This is the same as moving the magnet. So you saw in the notes where they were moving the magnet, they created current. Now we don't need to move the magnet. Now we can just change what the magnet looks like to this one. We can change what this magnet looks like, and it creates a moving magnet for this one. Even though this magnet is not moving, its magnetic field is changing, which makes it look like a moving magnetic field to this one. So the field lines are coming in and coming out, and they're changing. And when the magnetic field changes, it creates a current or a voltage. This galvanometer is a current meter. So it's reading how much current is changing in the wires.
inducing EMF in one coil through another coil is called mutual induction. And the magnetic and electrical interaction that occurs between two coils without any physical contact is called inductive coupling. Inductive coupling can occur in various ways. As we have placed two coils next to each other here, this is also a method of inductive coupling. We can see that when we flow a changing current through the first coil, the changing magnetic flux produced by the first coil is not fully linking with the second coil, which means that the energy of magnetic flux is being wasted. Let's say that only 50% of the magnetic flux produced by the first coil is linking with the second coil. To explain this fact, we use the coefficient of coupling, which is denoted by K. In this
You don't need
type
to worry
of
about
inductive coupling, where only 50% of the magnetic flux produced by the first coil is linking with the second coil, we would say that the value of K is 0.5. Now let's explore how we can obtain a better coefficient of coupling. Let's rotate the second coil in such a way that the axis of both coils is perpendicular to each other. Will this enable the magnetic flux produced by the first coil to link more effectively with the second coil? Let's understand this. As soon as we pass it.
So now what we're thinking is, okay, what if I have the magnet and I wave it past the front of the coil? What's going to happen? Is there any magnetic change going through the coil? What? The magnetic field is going like this, but it needs to go in the coil, right? So are we going to have any current created, David?
No.
Yeah, so the angle here is important.
Current through the first coil, a changing magnetic flux will be created. And as we can see in the animation, in this type of inductive coupling, the magnetic flux created by the first coil is not able to pass through the cross section of the second coil, which means that
What would we do if we wanted to keep this geometry but have the magnetic field lines turn and go through here?
Would you have to like turn the coil?
No, if we wanted to maintain this geometry. Not a wire.
Coil?
Marcus?
A conductor.
It's specifically a magnetic conductor, a ferromagnetic rod, or in the case of the Monday brain transformer, you would have a steel rectangle that just goes around like this, and the iron would not care. It would just turn the magnetic line this way. But we don't have that in this case, so.
no EMF will be induced in the second coil and no current flow will be observed in the galvanometer. For this type of inductive coupling, we will say that value of coefficient of coupling is 0. We can also understand this type of inductive coupling as the angle theta between the magnetic field vector created by the first coil and the area vector of the second coil being 90 degrees. We know from the formula for magnetic flux, BA cos theta, that theta is the angle between the magnetic field vector B and the area vector A, which is 90 degrees in this case. And it is clear that for an angle of 90 degrees, the value of cos will be 0, which means that the magnetic flux linked to the second coil will be 0, and the coefficient of coupling will also be 0. In other words, we are not getting better results with this type of inductive coupling. So let's now overlap the two coils on the top of each other in such a way that their axes become the same. And now, when we pass a changing current through the first coil, the magnetic flux created by the first coil will better link with the second coil. And this time, value of coefficient of coupling will be greater than last two cases. Let's say that K is equal to 0.8 this time. We can achieve coefficient of coupling even better, but it depends on the geometry of both coils and other parameters. We will understand the formula for K later in this video. Okay, Now let's define mutual induction more precisely. When a changing current is made to flow in one coil, a changing magnetic flux is produced in the coil. If this changing magnetic flux is linked with another coil, according to Faraday's law of electromagnetic induction, an EMF is induced in the coil, which starts the flow of current. The phenomenon of EMF and current being induced in the second coil due to the changing current in the first coil is called mutual induction.
Okay, that is what we are studying in this lab. Okay? When a changing current is made to flow in what we're going to call the primary coil, a changing magnetic flux is produced in that coil. Changing current, changing magnetic field. This changing magnetic field is linked to another coil. If the first one is the primary, what do you think we call the second one? Secondary. Secondary coil. Then according to Faraday's law of electromagnetic induction, an EMF is induced in the coil. This is a voltage. A voltage is induced, which starts the flow of current. So what we're going to do is, based on this, we're going to create a changing current in a primary coil and check the voltage in the secondary coil. All right? Now, he said there are many factors which affect this. We're going to talk about that in a moment, but there are many factors. Okay? And so, but this is the idea of what the lab is talking about. All right? Is it a whimper? All right. So, in Schoology, just so we're clear, these videos are listed. I thought we'd get to them last week, but they're listed in the week 7. Here we have the resources. This is let me refresh. All right. So there is the starter file and the data sheet, as well as I made it so you can turn it in. I haven't created the correct rubric to attach to this yet, so it doesn't have the rubric there, but I'll try to get to that. So the Faraday Lab guide